This is basic electronics engineering. The paper code is EC201. It has 3 number of lectures. Total contact hour is 36 and the total credit is 3. Myself, Dr. Indranath Shakar, Associate Professor, Department of Electronics and Communication Engineering at JS College of Engineering, Kolleri. Welcome to Module 2 of PN Junction Diode and its applications. There are 4 course outcomes of this subject. The first course outcome is to study the PN junction diode, ideal diode, diode models and its circuit analysis, applications of diodes and special diodes. Basically, our focus is to develop the growth of the students' knowledge on the foundation construction of the PN junction diode, as well as the different doping concentrations of the diode and the corresponding applications of the diode. So starting from the different model analysis of the diode for application in various types of circuits, we will carry out several mathematical examples which will give immense of knowledge to the students, so that students can play with diode, students can perform projects, create models using the diodes. The second course outcome deals with operational amplifier. Here our main focus is to develop the students' knowledge with the basic internal stages of the op-amp, so that students can freely demonstrate about the working principle of operational amplifier, starting from the basic amplifiers using op-amps such as the inverting and non-inverting amplifiers. Students will be able to create several types of circuits such as the differentiator, integrator, as well as buffer amplifier, instrumentation amplifier, so precision diode. There are various applications of operational amplifiers, and students can just play with op-amp so that they can create several types of projects using op-amp. And thereafter our attention will be towards the positive and negative feedback circuit. Here the students will go through the knowledge of the basic amplifier, and thereafter they will apply the feedback concept to the basic amplifier, so that they can enhance the parameters such as the input impedance, output impedance, bandwidth, gain of basic amplifier to some modified value. So feedback amplifier is another part of the control system which can give the idea of control system subject. The fourth one is dealing with the development and capability to analyze and design the simple circuit containing nonlinear elements such as the transistors, using the concept of load lines, operating points and incremental analysis. In this subject there are 5 modules. Module 1 is the basics of semiconductor, Module 2 is the PN junction diode and its applications, Module 3 deals with the bipolar junction transistor, and Module 4 deals with the field effect transistor. Module 5 is the feedback and operational amplifier. Module 6 is the cathode ray oscilloscope. Now here the chronological arrangement of the subject module will be beneficial for the student to grow the knowledge from basic foundation elements to complex circuitry using the basic electronics subject. The prerequisite of these subjects is the fundamental of electricity, direct current, devices and circuits, series and parallel circuits, to the study of active and passive components, Ohm's law, Kirchhoff's law, and KVL, KCL, Ampere's law, etc. KVL stands for Kirchhoff's voltage law and KCL stands for the Kirchhoff's current law. The course outcome, program outcome mapping is having several weightage depending on the high, medium and low, which are numerically weighted by 3, 2 and 1. We have an explanation of such course outcome versus program outcome, because program outcome is assigned by National Board of Accreditation. There are 12 program outcomes which are mapped to the course outcome. Now the first course outcome, as we have gone through, it is the study of PN junction diode, ideal diode, uh, diode models, its circuit analysis, its applications, as well as special diodes. The weightage has been given maximally to the program outcome 1 and program outcome 12. The program outcome 1 states that it applies the knowledge of mathematics, science and engineering fundamental and an engineering specialization to the solution of complex engineering problems. Similarly, program outcome 12 deals with the part, the lifelong learning, in which it is stating that recognize the need for and have the preparation and ability to engage in independent and lifelong learning in the broadest context of technological change. So as the basic foundation knowledge of this course outcome 1 which it dealt with, that is why it is mostly matching with program outcome 1 and program outcome 12, and there are medium weightage given to program outcome 2, 3, 5 and 11. Now the second program outcome is the problem analysis, and the third program outcome is the design and development of solutions, and the fifth one is the modern tool uses, and correspondingly 11th one is the project management and finance. So therefore these program outcome statements are getting the middle weightage, that means numerically 2 it is given. And the fourth program outcome is the conduct investigations and complex problems. Since we have minimum concept of start of the complex problem in this subject, because there is another advanced course, analog electronics, the students will go through in the fourth semester. They will be understanding in more detail, so that is why complex problems will be suitable in the analog circuit subject, not in the basic electronics. The main course objective of this basic electronics is to impart the fundamental knowledge to understand the basics of semiconductor and components like diode, transistor, FET, MOSFET and operational amplifier. It will build mathematical and numerical background for design of electronic circuits and components value. Students equipped with the knowledge and training provided in the course will be able to participate in design and development and operation in the different area of electronic system. So therefore the basic electronics subject is actually, in a nutshell, is the basic knowledge for the several components, so that students can know the characteristics of those foundation components, and knowing the characteristics of the component, students can apply this component for their own project or own circuit development. And during the circuit analysis, student can measure the parametric value of the component, so that they will understand the status of the component, whether it is giving correct value or it is giving the wrong value. So for this subject, a data sheet for individual component is also mandatory for students to see, because until and unless students go through the data sheet, they will not understand the detail of a particular component, because the data sheet gives not only the physical structure, dimensions, as well as various electronic parametric value for each and every component, and there are much more details given in data sheets because it is made by the manufacturer. We will discuss today the half wave rectifier and full wave rectifier. All the parameters will be discussed today. That is the DC current, RMS current, DC voltage, RMS voltage, ripple factor without filter, efficiency, peak inverse voltage, transformer utilization factor, reduction of AC ripples using filter circuits, etc. This is the block diagram for regulated power supply. As we know, for any electronics circuit applications, the regulated voltage is a must because we need a DC voltage in many circuit implementations. Without any DC voltage or without the availability of the regulated DC voltage, there are almost none of the electronic circuit is possible to operate. So how to produce such a regulated power supply? The block diagram is shown above. It is showing that 230 volt line AC is applied to the transformer, which is a fluctuating alternating current between the lowest magnitude minus Vm to highest magnitude plus Vm. So such a input waveform coming from the supply enter into the transformer. The transformer produces its output with certain amount of turn ratio, and finally it is reaching the rectifier. The rectifier has the responsibility to convert the positive sweeps and negative sweeps into unipolar, that means all are in positive sweep. Then they will be smoothened out so that we are getting almost positive voltage with little bit fluctuations known as the ripple fluctuation, and thereafter it is sent to the regulator so that the regulator will produce a fixed amount of DC voltage which may be applicable for load, because load requires fixed amount of voltage quantity. Therefore, from the AC signal to generate a constant voltage DC signal, such 4 number of stages are required prior to the load. There are essential parameters for the rectifier analysis which are listed below, such as the DC output current, the DC output voltage, root mean square current, root mean square voltage, rectifier efficiency represented by eta, ripple factor represented by the gamma, regulation, obviously voltage regulation, transformer utilization factor, and the peak factor. Now let us first discuss about the diode half wave rectifier. Now what is diode half wave rectifier? It is a simple diode followed by the load resistance. So whenever AC signal is applied to such a circuit, the diode is forward biased only for the positive half of the incoming AC waveform. But when there is a falling waveform, that means when there is a negative sweep present in the AC waveform, the diode is reverse biased, therefore diode will be switched off. So at the output of the basic half wave rectifier, we are getting the positive half cycle of the incoming signal, and there is no negative half cycle. So in the half wave rectifier, the diode conducts or forward biased only in the positive half of the cycle of the input signal, and so only the positive half cycle appears at the output. So let a sinusoidal voltage Vi be applied to the input of the half wave rectifier. Vi is equal to Vm sin omega t. So therefore we can easily find out that only the positive half cycle is present at the output. So if the current is I equal to Im sin omega t, which is producing positive signal for 0 to pi, and for pi to 2 pi the current amount will be 0. This is obvious because diode is working as a switch. When the diode is off, the reverse current, though it is negligible, flows. So that is why we can represent the current almost approximately equal to 0. And the maximum peak current is the ratio of the maximum peak voltage to the forward resistance and the summation of forward and load resistance. Obviously the forward resistance is the forward resistance of the diode. Now what is DC and RMS voltage? These are shown mathematically, how to calculate the DC voltage. As the diode is forward biased only for the half cycle, therefore for the half cycle we can integrate, and for the remaining half the integration is 0. So therefore we are getting the maximum magnitude of the current divided by pi is the DC quantity for the half wave rectifier. Similarly, for the DC quantity, RMS quantity of the RMS quantity of the output voltage is the half of the peak value of the applied input signal. Efficiency is the ratio of the output DC power to the input AC power for a rectifier. As we already have seen that the DC power can be calculated by the square of the DC current multiplied by the load resistance. So therefore DC current is again replaced by Im by pi, which we already have got the expression for the DC current. So squaring this ratio multiplied by the load resistance gives you the DC power. Similarly, AC power can be derived from the square of the RMS current multiplied by the load resistance. And if you consider the forward resistance, which is normally negligible, but if we consider, then we have to consider it along with the RL. That means RL plus RF will be considered, and therefore we are getting the overall power for the as a AC input power. Therefore, the ratio of the DC to AC power gives us the efficiency with the mathematical expression 4 by pi square into RL by RL plus RF. Now, normally load resistance is very high compared to the forward resistance, so load resistance by load resistance cancels out. So 4 by pi square gives you the efficiency for the half wave rectifier. So therefore, this ratio is normally 40.6. So for a very high load resistance, we can get the half wave rectifier efficiency is 40.6%. The ripple factor is one of the important parameter for half wave rectifier, which is the ratio of the AC signal to the DC signal. Now, AC signal may be represented as the square of the RMS minus square of the DC part. So therefore, with respect to the current or voltage, we can get the ratio regarding the ripple factor, which is calculated here. It is 1.21 for the half wave rectifier. The DC current, which is Im by pi, can be written as Vm by pi divided by Rf plus RL. Similarly, DC voltage can be given as the product of the DC current and the load resistance. So these are the important mathematical expression which is required for the calculation of the half wave rectifier. Another important factor is the transformer utilization factor. The secondary voltage is purely sinusoidal, hence its RMS value is 1 by root 2 times of the maximum, while the current is half sinusoidal, hence its RMS value is half of the maximum. Therefore, AC rated power can be given as the RMS voltage multiplied by the RMS current. So it is Vm by root 2 multiplied by Im by 2. So therefore, the transformer utilization factor can be derived as the ratio of the DC output power to the AC rated power, and it is 0.287 for the half wave rectifier. The form factor is another important parameter for the half wave rectifier, which is the ratio of the RMS value to the average value. So it is 1.57 for the half wave rectifier, whereas the peak factor is another important parameter for the half wave rectifier, which is 2 for half wave rectifier, because it is the ratio of the peak value to the RMS value. Now we are moving into the discussion of the full wave rectifier. The full wave rectifier is normally consists of two number of diode. One diode is forward biased for the positive half cycle, another diode is forward biased for the negative half cycle. So here center tap transformer is used for the secondary section. So whatever is the peak to peak variation of the AC input signal, it is proportionately coupled to the secondary with reference to the center as reference. So A and B part are simultaneously opposite polarity, because when A is positive at the time B is negative, when B is positive at the time A part is negative. So depending on that, any one of the diode is forward biased at one time, and that is why the current flows through the load resistance in unidirectional. Therefore, the DC value which is obtained at the output, uh, which is of unity polarity. The DC current expression for the full wave rectifier can be calculated for the full cycle. Earlier, in case of a half wave rectifier, we have seen for the half cycle it is having the finite value, for remaining half it is 0. The RMS value in full wave rectifier can be calculated considering the total cycle, that is total input cycle is required for the calculation. So the equation shows, which is straightforward, to calculate the RMS value of the current for the full wave rectifier. Finally, we got the value of this RMS current is Im by root 2. So gamma is the ripple factor, as we already have discussed. It is the ratio of the AC current to the DC current. So therefore, AC can be represented as the square of the RMS minus square of the DC, and square root has to be taken on the result. So that is why the gamma equation is given by the square root of uh, the difference taken between the ratio of the square of the RMS to DC current minus 1. For full wave rectifier, the RMS current is Im by root 2 and the DC current is 2 Im by pi. Therefore, gamma for full wave rectifier can be easily calculated, which is 0.483. The voltage regulation and efficiency are two important factors for rectifier. The regulation is given by the ratio of the difference no load minus full load to the full load voltage. This fraction to be multiplied with 100 to find out the regulation in percentage. The voltage regulation for the full wave rectifier can be calculated. It is the ratio IDC into RS plus RF divided by 2 Vm by pi minus IDC into RF plus RS. So regulation, if we calculate for the full wave rectifier, it is 81.2% as shown below. So here we have ignored the presence of forward and source resistance compared to the load resistance, because load resistance is dominating over the forward and source resistance. The filter in half wave rectifier is one of the important parameter which is eliminating the presence of ripple and produces constant DC voltage. So as shown here, the half wave rectifier for which the peak value is obtained for the positive cycle, and for the negative cycle we are getting no output. So if we use a capacitive filter at the output, then we can get the continuous magnitude. That is, it's a fixed DC magnitude, but there is a small fluctuations due to the capacitive charging and discharging. So therefore, the load resistance provides a discharge path for the capacitor in this base in the parallel condition, and because of the load current IR, there is a drop in the output voltage, which is called ripple. The peak diode current is much larger than the average load current. So Vd is equal to Vs minus V0t. So it is the source voltage minus the peak voltage of the input signal. Therefore, the maximum reverse bias across the diode is 2 times of peak value of the peak value of the input voltage. Now it is obvious, because if we check for a particular diode when it is conducting, the load voltage which is reaching the maximum input voltage. Now, so this is obvious during the presence of capacitor. Now one diode is forward biased, That is why the voltage across the uh, secondary terminal is Vm, as well as the load voltage is also Vm. So two number of Vm produces two times of Vm, and that is why when the diode is reverse bias, the voltage across the reverse bias voltage is two times of the peak voltage. And this is one of the disadvantage of the half-wave rectifier, because more is the reverse bias voltage, the chances of breakdown of the diode under reverse bias is more. And if this crosses the peak inverse voltage, then the chances of destruction of diode due to enormous heat for breakdown current may occur. That means diode may be burning out, causing the circuit damage. So therefore, peak inverse voltage has to be reduced under the reverse bias condition, whereas in case of half-wave rectifier, it is unavoidable. That means peak inverse voltage is two times of message magnitude. Now here the average diode current, which is calculated from the lower limit T minus Tc to capital T for the ID minus IR, that is the diode current and the resistive current. So when it is calculated, we are getting the average diode current using the charge balance situation. So the capacitive voltage, which is given by Vm into e to the 1 minus T by Rc, which is a decaying voltage, that is T tending to infinity, we are getting Vc is almost equal to 0. So for a long time, if the discharge is occurring in the capacitor, then it will be uh, tending to 0 volt. So Vc equal to T, Vc at T equal to Ts is given by Vm into e to the 1 minus Ts by Rc. So therefore, if we calculate further, we can get the capacitive voltage at the end of the discharge. So therefore, by considering the difference voltage, we can calculate the ripple voltage. So this type of calculation can be carried out for the full wave rectifier also. And later on, we will see that full wave rectifier is having advantage over the half wave rectifier, as full wave rectifier has more improvement due to the incorporation of the diode. So that is why the ripple variation is also reduced, and the efficiency can be increased for the full wave rectifier. Thank you.